Okay, in the last part of this section 4.7 material, we'll talk about finding the absolute extrema of a function of two variables. So in the problems that we've been considering in the first part of this section, we're finding local extrema of a function, but how do we find the absolute extrema? Or a better question to ask is, how do we know whether a function of two variables will have an absolute extrema? So to answer that question, we need to introduce a little bit of terminology. So let's start by defining some things. Here, we will start by defining a closed set in the plane as being a set which contains all of its boundary points. So what I mean by that is the set would have to contain its edge or its boundary in order to be considered a closed set. So graphically, in the xy plane, a closed set would be any region that contains its edge. So here, boundary points are these points on the edge. And as long as our set contains all of these boundary points, then it is considered a closed set. So this would be an example of a closed set. Now the opposite of a closed set would be an open set, which would be a set which does not contain all of its boundary points. So we might have the same sort of region in the xy plane, but if it does not contain the points on the edge or the boundary, then this would be an example of what is called an open set. Or more formally, an open set is any set such that if you choose a point within that set, you can find a disk centered at that point, which lies entirely within your set. Now, some other terminology that we need is a bounded set. So a set is called bounded in the plane if it can be contained in some disk. So if I can draw a circle around my set and it contains all of the points within that set, then it's said to be bounded. So here we can see that our first set, we could certainly enclose it in some circle. So this would also be a bounded set. And our second example of an open set would also be bounded. So what is an example of an unbounded set? Well, we could say, for instance, all of the first quadrant in the xy plane. If we consider all points with positive x and y values, we cannot enclose the first quadrant within any disk, no matter how large the radius. Therefore, this would be an example of an unbounded set. We have the following terminology, which allows us to then introduce the following theorem called the extreme value theorem, which says if we have a function f which is continuous on a closed bounded set D in the plane, then that function f we are guaranteed will attain an absolute maximum and an absolute minimum value on that set. Now recall that we had an extreme value theorem in Calculus 1 for functions of single variables. And the way that we would go about finding the absolute values of a function, or the extreme values of a function of two variables, would be to look at the function and where it would have its critical points within our closed interval from a to b, or we would look at the endpoints themselves. So for single variable functions, say the graph of a function f of x, we would have extreme values either within our interval, where we have critical points or 0 values for the derivative, or the endpoints could yield maximum or minimum values themselves. So in this case, we would have an absolute maximum at this point where our function has its largest value within the interval from a to b, and we would have our absolute minimum at that left endpoint of my interval when x is equal to a. So here I just want to make you recall that when we're looking for the absolute extrema of a function, we want to consider not only the critical values, but also the values of our function at the endpoints of our interval, say a and b. So how do we find the absolute extrema of a function of 2 variables? Well, we've got a little how-to process here. In order to find these absolute extrema of a continuous function on a closed bounded set D, we would start by finding the extreme values that lie in the set D. So we're going to look at the critical points within the interior of our set, and then see which of those critical points would yield maximum or minimum values. The next step is to then find the extreme values of our function on the boundary of our set, that is, on its edge. So just like we did for single variable functions where we had to consider the endpoints for a set in the plane, the endpoints would consist of the edge or the boundary of that set. Now, once we have the largest and smallest values in the interior of our set and the largest and smallest values on the boundary, the largest of those values would be the absolute maximum, and the smallest of those values is our absolute minimum. So let's look at some examples of finding these absolute extrema for functions of 2 variables. In this next example, we're asked to find the extreme values of f, which is this polynomial of x and y, and it is being considered on the closed triangular region that has vertices at 0, 0, 0, 4, and 4, 0. So let's start here by visualizing the closed bounded set that we're interested in. Here it was the closed triangular region with vertices at 0, 0, 0, 4, and 4, 0. So we're considering the part of the xy plane that lies in this closed triangular region. And we can see certainly it is bounded because we could enclose this within a disk. So to find the absolute extrema of this function over that set, we're going to start by looking for the extreme values in the interior of our set. So here, let's look for our critical points of this function. If we take our partial derivative with respect to x, we have 2 minus 2x, and we're going to set that equal to 0. And our partial derivative with respect to y is 2 minus 2y, which we also set to 0. So it follows that x has to be 1 and y has to be 1. And the point 1, 1 is indeed within our triangular region T. So we find the point 1, 1 is a critical point, which lies within the interior of our region T. Now our next step is to consider the boundary of this region T. And for a triangular region, our boundary would consist of the triangle with these vertices, 0, 0, 4, 0, and 0, 4. And the boundary of a triangle is made up of 3 line segments or 3 edges I'm going to call these edges E1, E2, and E3. So we're going to restrict ourselves to one of these edges, forming the boundary of our region, and see if we can find the critical points or largest and smallest values that would lie on each of these edges. So looking at our first edge, that is points on E1, we see that our first edge lies along the x-axis. So for any point on that edge, our y-coordinate would be 0. So our function of x and y is really just a function of x here. If we substitute 0 in for y, we're left with 2 plus 2x minus x squared, where the values of x can range from 0 to 4. So to find the maximum or minimum values of a single variable function, well, we recall from Calculus 1 that we would take the derivative of this function, which is now just a function of x, and set it to 0. So we have here 2 minus 2x would have to equal 0. So x could be 1. So we find that the point 1, 0 is a critical point. Now recall that we also had to consider the endpoints of our interval for these single variable functions. And in this case, the endpoints of our interval were x equals 0 and x equal 4. And so the other points which we want to consider along this edge, the endpoints, would be 0, 0, and 4, 0. So these are our points of interest on that first edge. So let's look at our second edge. On the second edge, E2, well, our second edge lies along the y-axis. So for any point on that edge, our x-coordinate is 0, and we're left with a function just in terms of y, which would be given by 2 plus 2y minus y squared, where the values of y can range from 0 to 4. So to maximize or minimize this function of a single variable y, as we did with the first edge, we would set the derivative of our function, which is 2 minus 2y equal to 0, and we find y would have to be 1. Or again, if we are considering as well the endpoints of our interval, when y is 0 or 4, we get a total of 3 points of interest. The first one being when x is 0, we found y equals 1, gives us a critical point. And then the endpoints of that second edge, or the endpoints of our interval, would be 0, 0, and 0, 4. So these are our points of interest on that second edge. So for our last edge, E3, let's think about how the points on that edge are defined. We see that every point on this third edge lies on a line, and the line is passing through 0, 4, and 4, 0. So this is a line which has a y-intercept of positive 4 and a slope of negative 1. That is the line 4 minus x. So on that third edge, our points are defined as lying on the line y equals 4 minus x. And so let's look at our function. F of x, y, well, if y has to be 4 minus x, we have 2 plus 2x plus 2y, which is 4 minus x squared minus y, which is 4 minus x quantity squared. So we're left with, again, a function that depends only on x, and if we expand this and simplify, we're left with the function negative 6 plus 8x minus 2x squared, where our values of x could range from 0 to 4. So as with the previous two edges, we can reduce our function to a function of a single variable x, and in order to determine where that function has its extreme values, we would take the derivative f prime, which in this case is 8 minus 4x, and set it equal to 0, giving us x is equal to 2, and y was 4 minus x, so y would also be 2. So here we find on that third edge, the point 2, 2 is a point of interest, along with our endpoints of our interval, when x is 0 or when x is 4. And here we end up finding the endpoints of that third edge, which would be 4, 0 or 0, 4, are also points of interest. Now, once we've found all these points, which are critical points or points of interest for optimizing this function, we need to determine which of these points yields the largest or smallest value of my function. So within this problem, all of these points that we found, namely 1, 1, 1, 0, 0, 0, 4, 0, 0, 1, 0, 4, and 2, 2 are all points of interest or critical points of this function. So let's take each of these points that we found and substitute them back into our original function f. So in the last part of our problem, if we evaluate f at these different points, starting with 0, 0, we have 2. As our next point, we could take 1, 1, and we get a value of 4. The value of our function f at either 1, 0 or 0, 1 is equal to 3. The value of our function at either 4, 0 or 0, 4 would be equal to negative 6. And for our last point, f of 2, 2, we get a value of 2. So once we find all these points of interest, we evaluate our function f at each of those points, and then the largest and smallest values that our function takes would be the absolute maximum and absolute minimum values. So in this example, we see our absolute maximum occurs at the point 1, 1, and the value would be 4, and our absolute minimum of negative 6 occurs at the points 4, 0 or 0, 4. So here we had a maximum at a point that was within the interior of our set, and a minimum on the boundary of the set itself. So let's look at another one of these examples, looking for the absolute extrema of a function over some closed bounded interval. This next one, we are asked for the extreme values of x squared plus y squared minus 6y plus 3 on the disk D, consisting of the points of all the points x, y, such that the sum of x and y squared is less than or equal to 16. So here, the set that we're restricted to is the disk centered at the origin of radius 4 within the xy plane. So we see from our sketch here that this is clearly a closed and bounded set, and our function f, which is a polynomial, we know is continuous on that set. So by the extreme value theorem, it must take an absolute maximum and minimum value, and we need to find these. So in our first step, let's look for the critical points of our function that would lie within this disk D. So we start by looking at our partial derivative of f with respect to x, which would be 2x, and we set this equal to 0. So x is 0. And setting our partial derivative of f with respect to y, which is 2y minus 6 equal to 0, we find 2y is 6, or y is 3. So here the point 0, 3 does lie within the interior of our disk, so we will consider that point in this problem. In this case, the point 0, 3 is a critical point. Now, once we find our critical points within our set D, we need to look at the boundary. So in this problem, the boundary of our disk would be the circle centered at the origin of radius 4. And the equation of that circle is given by x squared plus y squared is equal to 16. So let's consider our function on that circle. So we'll start by saying on the boundary of this set D, we have the circle x squared plus y squared is equal to 16. So our function f of x and y is given by x squared plus y squared, which we just said is equal to 16 for points on the edge of our disk. Then we have our minus 6y plus 3. So we're left with a function of y only. Here it simplifies to 19 minus 6y, where the values of y can range from -4 to +4, since 4 is the radius of our disk. Now, to find the extreme values of this single variable function, we would take the derivative of our function, that is f prime of y, which is -6, and we see here that our derivative can never be 0. So there are no critical points within the interval from -4 to 4 of this function, but we have to consider the endpoints of our interval as points of interest. So here, if y is positive or -4, then we could have points of interest, and if y is either positive or -4, it follows that our x value would have to be 0, since the sum of x and y squared must be 16 on that boundary. So here 0, 4 and 0, -4 are points of interest. So once we have found all of our critical points, or points of interest, in this case we have 3, the point 0, 3, 0, 4, and 0, -4, we need to evaluate our function at those points and see what our largest and smallest values are. So in this example, we have f of 0, 3 would be equal to 9 minus 6 times 3 plus 3. So we have -9 plus 3, or -6. And then the value of our function at 0, 4 would be 16 minus 6 times 4 plus 3. So we're left with -5. And for the value of our function at the point 0, -4, we have 16 minus 6 times our -4 plus 3 leaves us with 43. So here our absolute maximum would be 43, and our absolute